Thank you, Rory, and good morning, ladies and gentlemen. I'm here in behalf of my colleagues, the authors of this paper, who for different reasons and circumstances have not been able to be here this morning. And if you have seen the book of proceedings, the paper is full of mathematics, full of equations, matrices, and all that stuff. I will not go in much detail into that, first because I'm not well prepared for that. I will concentrate rather on the ideas, objectives, and concepts behind this work. But first, I'd like to start by paying a little tribute to my colleague, Raúl Monge. He's the main author of this paper. He passed away some months ago. Raúl was here in the LIV Symposium in 2015, talking about noise and vibration, which was his field of activity, and I'm sure he will have life to be here also this year. So wherever you are, thank you for your friendship. Well, my presentation is divided in two sections. The first one, I will try to put this work into context, into its general context and objective, which is the design of a semi-active roller guide system for lifts, for medium to high speed lifts. I will go through the design process we follow, and I will show you some results from simulations that were used for validation and from real test on real installation. And in the second part, I will give you some more details about this predictive compensator algorithm that we intend to use for this system. Well, as I said, the objective was the design of a active control system to reduce lateral vibration and lifts. We focus on this application range between 2.5 and 6 meters per second. It's not high speed, it's a medium to high speed range, which is very, from the point of view of our customers, it's very interesting from a commercial point of view these days. The first thing we did was to look at the state of the art. We analyzed different solutions, different patents already existing, and we found that they were based on many different configurations, many different control variables, many different actuators, and in general, they promise very good performance, especially in the high speed ranges. In most cases, they were aimed at that very high speed range, but in general, they were not commercially available. They used to be proprietary developments, seems to be expensive, and that's why we decided to develop our own system, more simple and more fitted to this speed range in which we wanted to focus. This is the general design methodology we use. It's called the B-cycle design process. It very much relies on simulation, includes software in the loop technologies in order to, as a way to develop the control design, and also hardware in the loop technologies to validate the system. Hardware in the loop technology is quite interesting. If you don't know about it, it's a technology which allows the combination of simulation results with real electronics, and then the outcome of the electronics are again input in real time into the simulation, so you can validate your developments quite easily, reducing the trial and error cycles that appears always in a design process. Anyhow, at the end, you will have to make a real experimental validation in real conditions. Well, using this design methodology, we came up to this concept design based on a standard roller guide arrangement, modified to include 3 semi-active dampers as the active elements in the system. For the control design, initially we use an acceleration feedback strategy using a skyhook algorithm for the control. And we try to build the system using standard and commercially available systems. First, a guide roller arrangement, in this case produced by ETN, a Dutch company. For the semi-active dampers, we analyze different possibilities, not only passive elements, but also active elements. And at the end, we select this kind of magnetorheological damper produced by Lord Corporation, an American company. This kind of damper are based on a fluid inside whose properties, particularly viscosity, can change when subject to an electromagnetic field. So you can adapt the characteristics and performance of this of the element through a electrical control. For the rest of the elements, accelerometers or other passive elements, we choose also commercially available systems, control system. And then we try to characterize experimentally every component in order to have enough input data for our simulation models to be used in this B-cycle design process that I told you before. So we characterize the guide rollers arrangement, the dampers and everything to be used as inputs in our simulation models that we use for a virtual initial validation of the system. Once all parameters were adjusted, we build the real thing and install it in a real elevator in a test tower and test it quite extensively, subject to different conditions, different deviation of the guides and different problems. We had quite a good response on the low frequency range when subject to different testing conditions. We made extensive trials. But I mean, we wanted to go further. We wanted to enter in a new field of control strategies based on predictive compensators. And even though initially the system was working as expected or as intended, we wanted also to use these models and these tools to analyze other control strategies, in particular predictive compensators. And for that, we first had to solve two problems. First, how could we estimate the geometry of the guides using non-very complex or very expensive sensors or too many sensors? We try to reduce the number of sensors and the accuracy of them to make them cheaper. And second, how could we manage all that information in real time so as it could be used in a active control vibration system? And here's where mathematics takes its role. That's the approach we took. We developed a perturbation observer algorithm based on Kalman filters. I will show you now. Complemented with a second algorithm to compress all this data, using, in this case, Mahalanobis distances algorithms, and both of them input into the active control system. As I said, for the perturbation observers, we use Kalman filters, which is a very interesting tool in areas of uncertainty. And here, uncertainty came from the limited number of sensors and from the limited accuracy of these sensors. And then for the mapping algorithm, we use these Mahalanobis distances, which tries to approximate a number of points through straight lines under certain error differences. You have all the mathematical details in the paper. These are the kind of results we had. deviation in the guide profile along the hive. You see that every 5-meter segments. Here are the results in this case, the same case, but with different rides, more than one ride. And here are the results we had when we implemented this group of algorithms in the control. These are results from a virtual validation. So this work is ongoing. So far, we have tested it on the using simulation. Next steps will be to validate it on real installation. So at the end, and as a conclusion, the main advantages of this approach is that it uses standard sensors already existing in the lift for car control or for other functions in the lift. It's an iterative algorithms, which means that it improves the accuracy with every ride and with every new set of data it collects in the troubles. It doesn't need big storage hardware, can work with this compression in real time. And it also can be used for other functions like, let's say, maintenance application, just to monitor the status of the guides, or for the initial validation of an installation. And well, that's all from my side. I just wanted to finish with this picture of Sixfield Stadium, where yesterday I think Northampton played against Manchester United. Unfortunately, Northampton lose, but I'm sure, for sure it was a great match. So,